Today, let's discuss the various challenges encountered when machining heat-treated materials. How can we reasonably select milling cutters and cutting parameters to improve machining efficiency? This is indeed a common issue faced by many in the mechanical processing field. Let's begin. First, what difficulties arise when machining heat-treated materials? What specific properties make these materials so difficult to process? Heat-treated materials refer to those with hardness ranging from HRC 35 to 60 or even higher, such as alloy steel, tool steel, and stainless steel. The first challenge lies in their high hardness and low plasticity, which leads to significantly elevated cutting forces and temperatures. This causes tool edges to chip or wear easily, resulting in short tool life. That does sound tricky. Are there other material properties affecting machining? Yes, they generally exhibit poor thermal conductivity. This causes heat to concentrate near the cutting edge, increasing the risk of thermal damage to the tool. Coatings also fail more readily, and the workpiece itself may deform due to heat, leading to dimensional deviations. Additionally, materials containing numerous carbides or hard spots exhibit intense abrasive wear on cutting edges. Combined with their high elastic modulus, significant springback during cutting generates vibrations that degrade surface quality and further reduce tool life. When aiming to improve machining efficiency with these heat-treated materials, are there any secrets to selecting tool materials and coatings? Absolutely. For tool materials, solid carbide is generally the preferred choice, especially the ultra-fine grain variety. For higher hardness materials, we recommend using CBN cubic boron nitride inserts or solid CBN tools. Another option is PCD polycrystalline diamond. Though it is typically used for machining non-ferrous metals like high silicon aluminum alloys, it is not suitable for machining ferrous metals or heat-treated materials. What are the considerations for coatings? The choice of coating is also crucial. Generally recommended are high-temperature resistant coatings like Tlain and Alkern. For hardness above HRC 50 or intermittent cutting conditions, coatings with high aluminum content are particularly recommended, such as Alton or Alkern. Additionally, nano-multi-layer coatings like Alton or tin demonstrate exceptional resistance to abrasive wear and thermal shock. How should cutting parameters be reasonably set during actual machining to maximize both efficiency and tool life? This depends on whether it's roughing or finishing. For roughing, prioritize increasing feed rates rather than solely boosting cutting speeds. Maintain moderate cutting speeds and feed rates with slightly reduced depth of cut to minimize impact and vibration. For interrupted cutting, further reduce the cutting speed to prevent frequent thermal shock to the cutting edge. How should these parameters be adjusted during finishing operations? While finishing allows for slightly higher cutting speeds, fine-tuning must be based on tool material and machine rigidity. Feed rates should be slightly reduced to ensure surface quality. Cutting depths are typically minimal, ranging from 0.1 to 0.5 millimeters, depending on actual conditions. A fundamental principle here is to prioritize deeper cuts at slower speeds over shallow, rapid passes. This prevents the cutting edge from friction polishing the material surface, which can lead to excessive heat buildup. Beyond cutting tools and parameters, what improvements can be made to machine tools and clamping systems to enhance machining efficiency and quality? First, ensure the machine tool possesses sufficient rigidity and power, ideally using a machining center or a CNC milling machine with exceptional rigidity. Next, minimize tool overhang by using thicker tool shanks and pairing them with high-rigidity tool holders such as shrink-fit chucks, hydraulic chucks, or heavy-duty spring collets. Workpiece clamping must also be exceptionally secure to minimize vibration and deformation. Are there any specific considerations for cooling? If the machine tool permits, prioritize high-pressure internal cooling to direct coolant flow onto the cutting edge. Additionally, select coolants suitable for high-speed cutting, such as cutting oils or emulsions containing extreme pressure additives. For dry cutting with CBN tools, minimal air cooling or oil mist cooling can be used to prevent thermal shock. What specific considerations in the entire machining process can help us improve efficiency? A crucial principle is to complete most rough and semi-finished machining before heat treatment. After heat treatment, focus only on finishing critical dimensions and performing localized rework. This approach minimizes the machining allowance required post-heat treatment. For instance, most contouring can be completed in the soft state, requiring only minor finishing after heat treatment. This avoids large material removal at high hardness, particularly preventing extensive slotting or roughing operations involving interrupted cutting. Next, we'll discuss how to select the appropriate milling cutter for different heat-treated materials and various machining processes. For example, when machining mold steel or alloy steel with the hardness of HRC 35 to 50, what type of milling cutter should be selected for roughing and semi-finishing operations? In such cases, solid carbide end mills are generally recommended, specifically 4 or 5 flute cutters with a helix angle between 35 and 45 degrees. This configuration effectively accommodates a wide range of milling scenarios. For applications involving significant impact loads, adding a guide edge to the cutting edge can enhance its impact resistance. When seeking options for deep cutting depths, high feed rates, and efficient rough machining, consider indexable end mills equipped with P30, P40, or carbide inserts specifically designed for HRC 40 plus hardness, combined with the Tyone coating. For finishing operations, solid carbide end mills with long cutting edges, typically 4 or 6 flute designs, are generally selected for refining side and bottom surfaces. For machining mold cavities or curved surfaces, ball nose cutters are preferred. When encountering harder materials, such as brittle hard tool steels or high-speed steels in the HRC 50-65 range, how should one select the appropriate milling cutter and machining method? For rough machining of such high-hardness materials, solid carbide end mills with reinforced cutting edges are typically selected. These are used with shallow cutting depths and multi-pass machining. Alternatively, indexable CBN inserts can be employed for rough milling, which is particularly suitable for machining flat surfaces and step surfaces. For semi-finishing and finishing operations, small diameter solid CBN end mills with diameters ranging from 2 to 10 mm are typically selected. These tools are particularly well suited for precise machining of critical dimensions and surfaces. For flat milling or contour milling, indexable CBN inserts are still preferred, as they enable higher cutting speeds than carbide tools, thereby improving machining efficiency. To wrap things up, what are the key points that can help us improve cutting efficiency when dealing with these difficult-to-machine heat-treated materials? The core lies in 3 points. First, select the appropriate tool material and coating based on the material's hardness and abrasive wear characteristics. For instance, use cemented carbide paired with high-performance coatings or opt directly for CBN tools. Second, establish appropriate cutting parameters. Generally, it is recommended to use a moderate cutting speed, a larger feed rate, and an appropriate depth of cut. This combination is ideal. Third, enhance the rigidity of the machine tool and work holding fixtures. Ensure adequate cooling, and optimize the machining sequence. Whenever possible, perform more rough machining before heat treatment to reduce the machining allowance required after heat treatment. Achieving these 3 points will significantly improve machining efficiency and tool life.